this is actually the coolest Excel spreadsheet in the entire universe. And what I want to show you here, okay, right here is the spreadsheet, or this is the Gaussian distribution right here, and also right here. So what this does is I can, right here it shows the mean. Well, right now it shows the mean at being at 10. Well, that's not the standard normal distribution. Let's make it be the standard normal distribution. So we can go up here. Okay, anyway, so we're going to make this, the mean be at 0. Can you see how that changes where this mean is? Watch down there when I change it back to 10. Oh, well, I guess you can't see that, but we're going to, okay, move it back here. See, now it's at 10, and then we're going to move it back to 0. Now if you look, oops, I have to get out of that. Now if you look, it's now it's at 0. So now let's change the standard deviation, and I think we might be able to watch it do this. You're going to see as I make it into 1, it should narrow a little bit. So, did you see that? Narrowed. Okay, so this is a little bit narrower now. Now notice this is the cumulative distribution function. So what this is saying is at this coordinate, which is 2, we have an area of 0.9726 that is encompassed by this within that's less than 2 standard deviations. Let's try, let's see, we're gonna let's take this down to right here. Can you see now we're at 5.5? And look at this. Here we are, we're, well, just a skosh more than 0.5. So now let's make it well, there we go. We're right at, wow, is that good or is that good? Now that's 0.5, and that's the area here, and this curve right here, that just shows what that area is. We can always find what that curve is by simply using the table of the normal distribution, right? So all we have to do is know our z-value, and then we can go directly to the table and find out what the corresponding area is for that z-value. So let's see here. Here we go. This is the table, which is a little hard to read, but if you take a look at it, it shows you, like, if z is minus 2.44, you can see that the area that's less than that curve is only 0.0073. So that's a quick review. Okay, one thing I want to talk about right now is the special values for the normal distribution. And those are that if we're 1 standard deviation from the mean, that's, see how it says plus or minus 1 sigma, that's 1 standard deviation, then this area right here is going to be 0.683, so 68% of the, the total value under the curve. And then if we're 2 standard deviations, that's this light blue line right there, 2 standard deviations is going to get you 0.955, so it'll be 95% essentially. And 3 standard deviations is 0.9967. So these are special values that we often refer to. Look at what this is saying. If we take, as is the usual convention, the mean, let's see, plus the standard deviation from the mean, so if we go, here's the mean right here, and we go up 1 standard deviation, that's sort of the same as saying we're actually the mean plus one standard deviation. So if we plug it into that z-value formula, it's mu plus sigma minus mu over sigma. Well, look at this. It's actually converted into the z-coordinates. It's the cumulative distribution for z at 1 minus the cumulative distribution for the z at minus 1. So that's plus 1 and sigma's minus 1. So you subtract those two areas, there you go, 0.68. So approximately 2/3 of the outcomes from a normally distributed random process will be within one standard deviation of the mean. So that's not too bad. And likewise, if we play the same game and we go 2 standard deviations away, so we're up 2 standard deviations from the mean, subtract that from the mean, and then divide by sigma. We're normalizing essentially. So we're going to have converted into the cumulative distribution function on the z scale. It's the cumulative distribution function at 2 minus that at minus 2, and if you subtract away, that's 0.9545. So what this is really doing again is we're here going like this. Oh no, we're not going like this, because if we do, it's a terrible curve. Okay, let's try again. You try drawing with your hand way away and you can't look at your hand and it's on the screen and it's harder than it looks. So anyway, so 0.95 means we go 2 standard, here's the mean, here's maybe 1 standard deviation, and here's 2. And likewise, here's minus 1 and minus 2. And so all of this area right here, this whole shebang, is going to be an area of 0.95. So what is this area? What would it be in blue? Yeah, this would have to be 0.025. And the black right here, what would that area have to be? 0.025 again. Yep. So there we go. These are just special values. And then likewise, if you look again at 3 standard deviations, it's the same idea. Here's our little curve, except now we're 3 standard deviations, so it's going to be a teeny tiny area out here that's left out, crippled. It couldn't join the rest of the crew. So you can see that take this value from 1, so 1 minus 0.9973 divided by 2 is going to be this area right here, and the other one will be also the same area. So I think those are important special values, and the final important special value is 6 sigma, right? And that just involves this minus and plus right here. So you can see it actually will encompass 0.99, a bunch of 9s. So essentially, if you're at 6 standard deviations, only 2 outcomes per billion will be more than plus or minus 6 sigma from the mean. So with that, let us take a look at this problem. So here we go. What's the probability that a sample strength is less than 6250? Well, all we have to do is use our magical formula, which is z is equal to x minus mu over sigma. And then we're going to translate this into z-score. So because remember, if we wanted to, we could actually have a chart that had as its mean the 6,000 kilograms right here. We could have 6,000, and in fact this is what the actual distribution is, and the standard deviation is 100, so 1 over would be 100, kilograms off to the side, and this would be 200 kilograms. But we don't want, so we could say there's a 50% probability that it's going to be less than 6,000 kilograms, but we don't want to make up a table for that area. So instead, we translate it to Z chart, so we'll make our Z extra special, bright, flashy red, and it's actually the same thing, magically transformed. So now our mean is set at 0. And our standard deviation is set to 1. So we do this translation by using our magical formula, that maps this onto this. And so we can say, what was it, 6250 minus 6,000 all over 100 is equal to our new z-score, which is 2.5. So what's the probability that a sample strength is less than this value? Well, let's see, here's 2. So it's going to be this whole area under here, which if you look on our magical table, everything's magical today. We're going to look over here at, we need to find 2.5. Do I have it here? This. Okay, so now we've got a positive Z table here, and we're looking, and I'm bringing this, I hope, over a little bit. So I just want to make it really clear. Here we go, there's 2.5, and you're going to read off of this first one, this first column. And that first column is, if you look at the very top of it, I got to move it over a little bit but look here, the very first column is 2.50 or 0.40, right? Because this column gives the the 100th place. So we got that, and so 2.5 is 0.9938. So going back, we can find this is going to be an area of 0.9938, and that's the probability that a sample strength is less than this value. Now, what is the probability that a sample's strength is between 58 and 59? All we have to do is translate these values to z-scores. So it's going to be what, 58, that's here, that's 5,800, and this is 5,900. So that's in real life. It's going to be between these two, it's going to be that area. And remember, this whole thing underneath that curve is 1, the possibility is 1. So so all we have to do again is translate this into z-scores. So we'll do that. Translate. Okay, here we go. Our new is z for the first is 5,900 minus, whoops, let's see, is that going to show? Yeah, I think so. 5,000 over 100. So what did you get for a z-score? Minus 6,000. Yeah. Planet we were on, we're now back on the appropriate planet. So z is now minus 1. So now 5,800 minus 6,000 all over 100 is going to be what? Minus 2. So this is minus 1, this is minus 2. We just need to take the area, remember this z-score from the -1, if we look it up, now I can actually use the appropriate table. So z is equal to -2.0 is -2.0 is 0.0228. This one is 0.0228, and this z right here, oops, let's do some erasing. So the z is equal to -1 is affiliated with an area of, we go here, look at -1.1587. So it should be on your tables there. 0.1587. Whoops, 7. So this small area right here is that value. This area includes both values, right? Because it's okay, let's try this again. This area right here in black is the small area, and this area, which is all of it, is right here. Okay, so then we just subtract 0.1587 minus 0.0228, and that's equal to 0.13591 if you want to be. So that is the probability that the sample strength is between these values. Okay, so lastly, what strength is exceeded by 95% of the samples? Now the key word here is exceeded by. So that means, and you'll notice the screen has miraculously been cleared, that in, okay, I'll try this again, that with our curve, still not very good. Okay, exceeded by 95% of the samples. We need a z right here, where 95% of the samples are bigger than that. That z, as it turns out, is the z that has 0.05 or 5% of the samples smaller, right, or with less strength. So what we need is a z that has an affiliation with a sample size of 0.05, or an area there that is 0.05. So let's go look that up. Here we go. So I'll bring this over here so you can see. Okay, what area inside here is going to be affiliated with a z value? And that area has to be a 0.05. So first let's find 0.05. Let's see here, should be right around here. Okay, so 0.05. Okay, so it's, look at here, right around 0.0495 or 0.0505, one or the other. And if we go look, that's going to be at what? Right around minus 1.60, 1.61, 1.62, 1.63, 1.64, 1.65. So we'll call it 1.65. So take our little table, put it out of the way, and now we'll say z is equal to minus 1.65, right? Because actually I didn't point that out before, but see, there's a minus 1.65 or 5 there. So that z value is affiliated with being exceeded by 95%. Now, all we need to do is translate that z value into an actual sample size. So we use our magical expression. So z is equal to x minus mu over sigma. We know that z is equal to minus 1.65 and equals x minus 6,000 all over 100. And then we solve for x. And we find that x is equal to 35 kilograms. Voila! Now, if you really want to see how x is applying here, it's the same as, this is the z characteristic, right, is minus 1.65, and that's the same as if we had a mean that was at 6,000 kilograms and we had a sample that was 5835 right at that point, right? And then 95% of the samples would have a strength that exceeded this 5835 kilogram value. Here we go. Here's our practice with normal distribution. So which of the following data sets is most likely to be normally distributed and why? Here we go. The handspan of a random sample of OU students. If you look, we've got, your typical hand. That's a typical hand, right? If you measure that distance from one to the other and you find it's really big, then you're probably going to be a good piano player. But you can see that probably there'll be a mean of how that's distributed, and some people will be less, some people will be more, and it is probably normally distributed. Annual salaries of all employees at Ford Motor Company. It probably has a distribution kind of like this, right? Or, well, maybe higher here, but it'd be a narrower standard deviation. So you're going to have, depending on what pay grade you're in, there's going to be a lot of people in this pay grade, a lot of people in this pay grade, a lot of people in this pay grade. So it's not going to resemble just your your standard normal distribution. So the annual salaries of a random sample of 50 CEOs, 25 men and 25 women. That's probably going to be pretty random. I mean, pretty Gaussian in how it's going to look. The dates of 100 nickels from a dash drawer in a convenience store. Well, you're probably going to have, you're going to have a lot of ones that are like recent, and then it's going to kind of drop off like that. So the older it is, until you get down to a 1873 penny, forget it. You're not going to get it. So it's actually going to drop off to zero. That just gives you a sense of the kinds of things you could find in real life. So we actually have already discussed this excellent Excel visualization. So when you go in and grab your copy of the PowerPoint, you can go and play with that one video yourself. Let's see. So let's look at it for just a minute, a little bit more, and we can change the mean however we want. So we can make it so the mean is at 15, and we've got a standard deviation of, I don't know, 10. And with 10 makes it a lot wider, and again, the area under this curve is just given by this cumulative distribution function. And our problem is we don't have a simple formula for that cumulative distribution function, so that's why we have to go and use a table. Okay, so a new problem for you. If we want to, well, first off, what is 4 hours in minutes? We got to translate it. Okay, so it's 240 minutes. Okay, so the probability that the battery lasts more than 4 hours or 240 minutes, well, if we look at it, okay, so 260 is here, so 240 is going to be somewhere down here. So we know that whatever happens, we're looking for something that lasts more than this value. So we're actually looking for this value right here, the green. So it's going to be bigger than 0.5. You know that, because it's down here at 240. This value's got to be bigger than 0.5. So solving it really quickly, it's going to be this Z value right here is the one where the battery lasts more than 4 hours. It's in the green section. Yes. So whatever that Z value is, if we can figure that out, we can figure out this red part, and then one minus that is the green part right here. So we'll say Z is equal to 240 minus 260 all over 50. And that Z value turns out to be, what did it turn out to be? It's 0.4. Yeah. Okay, so then when we go and look at minus 0.4 and see the area affiliated with that, and we've done enough problems now, so we should be able to. So what was the area affiliated with that? 0.3446. Okay, so now we take, to find the green, we take 1 minus 0.3446 and find 0.6554. And so what's the probability the battery lasts more than 4 hours? It's 0.6554. What are the quartiles? What we want to do is this area right here, we want to be 0.25. So we find the Z-score affiliated with 0.25. So we go look negative table, so we will look that up. Here it is. Okay, 0.25. We look over here, 0.25. Yeah, it's somewhere right around here, 0.25. So it's negative 0.601234567. Negative 0.67. So negative 0.67. That's our Z-score. And if we translate that Z-score into, so we can say negative 0.67 is equal to X minus, what is our mean, is 260 over 50. And we solve for X. Then X is going to be 26.28 essentially minutes. Okay.